Pattern recognition is a fundamental component of intelligence. For example, if an animal, let's say a deer, sees a pattern on its retina, it had better be able to tell the difference between food, let's say a tasty clump of grass, a mate, in other words a deer of the opposite sex, or a predator, for example a tiger or lion, or else it's going to be in trouble and won't be able to survive. Pattern recognition is equally important for simpler animals. Even an amoeba needs to be able to tell whether the pattern of chemicals surrounding it indicates the presence of food or a hazard like a toxin, or else it will not be able to survive. You can probably see from these examples that pattern recognition is the simplest but probably the most important type of primitive intelligence. And patterns and their recognition are equally fundamental to artificial systems as well. For automatic reading of text, we need to recognize the pattern that each letter makes in a picture, or the patterns of sound representing a word in speech recognition, or, to give you some more abstract examples, for instance the patterns of readings which mean that a machine is faulty, or the pattern of biometrics, for instance blood pressure or heart rate, which is an indication of a medical problem like a heart attack. Now, the reason that I've laboured this point is that pattern recognition is one of the main things which ants do. To see how, let's take an example. Let's say that we have an image which is made up of 4 pixels, as shown in the diagram. Pixels are the dots which pictures are made up from. When an image is focused onto the back of your camera by the lens at the front, millions of tiny sensors read out the light intensity at each point in the image. If an image is divided into, say, 1,000,000 points or 1,000,000 pixels, we say that it's a 1 megapixel image. Although our example here only has 4 pixels, the principle is exactly the same. The light intensity of each pixel is often represented as a number between 0 and 1, with one extreme, for example 0, representing white, and the other extreme, for example 1, representing black. Now I can connect up a simple neuron to the pattern which is shown on the screen, and through common sense set the weights so that it produces a 1 output for this pattern, which signifies that it recognizes it. In this case, the sum is equal to the input 1 times weight 1 plus input 0 times weight 0 plus input 1 times weight 1 plus input 0 times weight 0, which is equal to 2. And since 2 is greater than the threshold of a neuron, which is 1.5, then the output is equal to 1, and therefore the neuron recognizes the image. But crucially, if I put a different image into the same neuron, it won't recognize it. 2 examples of this are shown on the screen, using exactly the same principle as I used for working out the last one. So the neuron can recognize a pattern, the very basis of simple intelligence, as we've already discussed. All I have to do is to set up the weights properly. If this simple neuron were fed from, say, a simple camera on top of a robot, it could therefore recognize obstacles in the robot's path. Furthermore, and importantly, the neuron will recognize the pattern even if it's corrupted, noisy, or imperfect. This is shown on the example on the screen. I hope that you can start to see the power and purpose of the ant from these simple examples. In reality, the weights of the neural network are set automatically using the training or learning algorithm, which I'll describe a little bit in the next video. Of course, in these simple examples, I've glossed over a lot of subtleties, problems and issues with real patterns and real neural networks. But don't worry, we will come back to these and discuss them in detail in the coming videos.